Welcome back, everyone. And now we will move to our next speaker, Dr. Ramzi Halabi, who will be talking about deep cardiology, multi-channel electrocardiogram classification and edge deployment. Dr. Halabi is a lecturer at Rafik Hariri University, a research scientist, and he's also a biomedical, electrical, and computer engineer, and the chief technology officer at Wiglo, a startup company creating a wearable non-invasive glucometer. Welcome, Mr. Halabi. We are so happy to have you with us. Feel free to introduce yourself and start with your presentation.
Thank you so much, Ms. Noor. Can you hear me?
Yes.
Okay, so I can see that you are live streaming. Do you want me to open the camera, or is it okay to leave it closed for bandwidth?
You can do whatever you want. You can keep it, you can open it and you can.
Okay. Kindly confirm that you can see my screen.
Yes, I can see your screen.
Okay, so thank you so much for the introduction. Thank you for allowing me to lecture in this very nice event, which is organized by Beirut.AI and by the MENA region administration for this kind of global events. Thank you so much. It's an honor and a pleasure to be a participant in this and a workshop lecturer. My workshop will be a 2-hour workshop. We called it workshop because it will be hands-on. So everyone, kindly, if you wish to code with me, if you are fast coders, I think that you will be okay. However, 2 hours, as you know, are not enough to write maybe just a pre-processing chunk of code in some cases. And I do not really have a full background about your backgrounds. So who is an expert in AI, who's not? I hope to meet you very soon, all of you guys. Thank you so much for attending. I will be sharing codes, I will be sharing links. So this will be very interactive. If I ask questions, I hope that you can hear me well so that you can answer. Try to take advantage of these 2 hours. I will try to summarize a very, very difficult field of deep learning that is nowadays not very well established. It is being developed. However, the machine vision part is more developed. So the title of this workshop is Deep Cardiology, Multi-Channel Electrocardiogram Classification and Edge Deployment. Firstly, I do not really like to talk about myself, so I made it very short. My name is Ramzi Halabi. I have a PhD in signal processing applied to biomedical engineering. I am a research scientist and a lecturer at Rafik Hariri University. I teach biomedical engineering. I teach electrical, computer and communication engineering, and I used to teach industrial engineering and mechatronics as well. I have expertise in signal processing, image processing, machine vision, machine learning, typical machine learning, deep learning, advanced biomedical signal processing, neural engineering, and wearable medical device design. So this mixture, I think, is a good mixture for this lecture so that I can give you a wide perspective about it. And if you have any questions, I hope that I will leave you some time to ask questions and to have answers that are well suited to your applications. So this is it. My previous background, BSMS, was in biomedical engineering and more into biomedical instrumentation. And then I did a PhD in Université de Lyon in France in signal processing applied to biomedical signals. And I got multiple certifications, whether it were academic or professional, in neural engineering, signal processing, deep learning, and several research awards. So my experience is from 2011, so it's like 10 years now, and hoping to get better and better, and keep in mind that we are always learning. So I'm not stating this to seem as a teacher. I'm a student just like everyone who is currently studying, and some students might be even better than me, and it's fine. So what's the outline? We're gonna be talking very briefly about some concepts, because I want to focus on the workshop side of this session. So we will be starting with electrocardiography, which is known as ECG. Then a bit about machine learning, then time series classification, what is the state of the art right now, and then deep learning for time series classification. So when I say TSC, it is time series classification. And when I say DL, TSC, it's deep learning for time series classification. So electrocardiography, what about electrocardiography? What is it? Typically, they all get pictures of models. I will not. I like to change a bit of mood for you guys. So this is a typical montage for a 12-channel ECG system. It is a system that allows you to acquire the electrical activity of the heart and the different polarization vectors of the electrical activity of the heart all across the body. This is the maximum that you can get, 12 channels. This is what makes it a lot challenging in terms of deep learning, in terms of machine learning. The amount of features, the amount of parameters that you will have in your model are a bit huge. So how do we get 12-channel ECG signals? What you have to do is to connect a number of electrodes that you will see right now. We have the right arm, right leg, left leg. Usually the right leg is considered as ground, and you will have RA, LA, and LL as your Einthoven triangle. So these will get you lead 1, lead 2, lead 3, and the augmented leads AVR, AVL, and AVF. Then you connect electrodes over the chest, and we call these positions V1, V2, V3, V4, V5, V6. And for the medical students or medical doctors who are watching right now, you know the actual anatomical terminology, so no need to mention it. Intercostal space to the right of the sternum, fourth intercostal space to the left of the sternum, directly between V2 and V4, intercostal space at mid-clavicular line, and so on. This is the actual anatomical and technical terminology for these. So these are 6 electrodes, and we had 4, it makes it 10. 10 electrodes that gets you 12 channels. Some channels are directly got from and acquired from your electrodes. Some others are like the augmented leads, AVR, AVF, AVL, are computed via equations or via formulae that are taken from the other leads. So if you have lead 1, lead 2, lead 3, you can get the augmented leads. No need to have extra acquisition schemes in order to get them. What is the electrocardiogram now? So when I say electrocardiography, it's the science behind it. The science of reading or acquiring the electrical activity of the heart is called electrocardiography. The machine that gets it is called electrocardiograph, and the signal that you get out of it is the electrocardiogram. Okay, so electrocardiogram. They're all called ECG. The field is ECG. The machine is an ECG machine, and the signal is an ECG signal. So it's that final letter or several letters that will differ. So this is the heart. You have the atria and you have the ventricles. And then when contractions happen due to electrical impulses, involuntary electrical impulses, you will have this polarization, depolarization, and repolarization of the heart. So what happens is every heartbeat is actually a PQRST, and some call this small microwave, they call it U. So PQRSTU. When you use your smartphones, when you use any device, in order to get the heart rate, you just need this. So you can just measure pulse rate or measure the pulses and know what your pulse rate is and heart rate is. In this case, we have PQRST, it's the whole segment. So now, let's consider this signal, and I'm going to elaborate more now on how to interpret this pattern so that we understand what we'll be doing until the end of the session. So this is the PQRST, and this is called U, as I told you. And then you will have another. So it's like a sequence of heartbeats, and it keeps beating until a certain time. So when this is beating, we will have contractions and relaxations of the muscles. We will have electrical manifestations. And out of this signal, we can get a lot of features. We call them time domain features, frequency domain features, and time frequency domain features. Time features like what is the maximum peak, let's say. What's the peak of your ECG? Time features like the heart rate. Time features like the heart rate variability. time features like the ST segment or ST interval duration, the amplitude of the ST. It might be elevated, we call this ST elevation. It might be depressed, we call it ST depression. And you will have PQ intervals, PR intervals, RR intervals, QRS interval. All of these are time domain features. If you perform Fourier transform or other transforms, you will get into the frequency domain or spectral domain, in which you can get the spectrum of your signal and know the maximum frequency, median frequency, and so on. Time frequency, it's the variation of the frequency components in function of time. So how are these frequencies varying in function of time? Using short time Fourier transform, using wavelet, and so on. So what we do usually in machine learning, we take these features that I told you about, ST segment duration, RR interval duration, QRS duration, peak amplitude, T amplitude. All of these are considered as inputs for our feature engineering section of the code, where you choose the best features out of these, and then you use them as inputs for a neural network or a machine learning algorithm until you get a class. However, what is the problem? The problem is the fact that we are not expert enough and we are not observant enough to observe all kinds of details and all kinds of minute and intricate details of this signal. Because in the codes, or using the codes that I will be showing you, the machine learning or the deep learning algorithm surpassed physicians. Expert cardiologists were not able to get the accuracy that the deep learning system has got. This is by itself something that is astonishing, actually. If you get experts in cardiology who have 20 or 30 years of experience, they will not be able to distinguish minute details that the deep learning system can distinguish. This is why we are motivated about this kind of application. And I hope to be giving you a good introduction today. So what is machine learning? We have a typical machine learning pipeline, which is getting your data. Your data can be got from different sources. You can get it from the device and directly acquire it and start performing on-the-fly processing and analysis using, let's say, a microcontroller. You are familiar maybe with Arduino, maybe a mini computer like the Raspberry Pi. All you have to have is a sensor and an instrumentation amplifier or a set of instrumentation amplifiers and a couple of filters, and you are good to go. You can get your signal. If you want to do offline analysis, you can have access to a database, an online database, over which you have signals, or you can download them from very well-known resources. What are these resources? I will make sure to give you everything you need to start off your career in this track, okay? So bear with me, keep focused. I will try to give you everything, even if I will not go deeply into everything because we don't have time. I'll try to give you a glimpse about everything. So let's say that we got our data. Now we need to analyze it, or actually before you analyze it, you need to filter and you need to process in typical ML. Then you get your features, and then you perform feature engineering. Feature engineering means I will not take my features as they are. What if these features are redundant? So let's say you took 100 features out of your ECG. Who said that these 100 features are all pertinent and relevant to your outcome? Who said that the ST elevation, or let's say RR interval, differs from a normal versus an abnormal heart? Who said that? Maybe in certain diseases, certain anomalies, but not in all. So you are throwing in data into your system that you do not actually need. Therefore, you need to perform feature engineering. It might get you from 100 features to 3 features. That will get you up to 90 and 98%, or maybe 100%. I don't like this 100% actually. I like 98, 99, because 100% you're definitely overfitting. I see that we have some chats. Yeah, of course. So Ahmed is saying that certain features are correlated. Exactly. So what we're saying is I'm giving some examples about the problems that you might encounter prior to performing feature engineering. You might be getting features. However, these features are getting you to the same point. So these features are correlated together. If one increases, the other increases. If it decreases, the other decreases. So what's the use? We call them redundant features. You are having redundant information. You are getting so much information into the system, adding complexity and computation cost, but you are getting nothing out of it in terms of added value, in terms of accuracy, precision, F1 score, and so on. So what we do is data pre-processing and feature engineering. We clean our data. This is the informal way. We clean our data until we get into a feature vector that we know for sure that it is the optimal one for this application. So feature engineering, feature selection, and then we go to the machine learning model building. And I will not go into the several hundreds of machine learning algorithms that you might find. I'm saying hundreds, it might be inaccurate. There's a lot of machine learning algorithms that you may use. It depends on your application, on your input type, on the goal of your research. And then we build the model and we evaluate it over our data. This is the typical ML pipeline. Now, before I go onto the next step, what is the problem? As I told you, the problem is when we do this, when we do data analysis, feature engineering, and so on, who said that the features that I got are the only ones that will get me to my result? I'll tell you the contrary. You might get features that will deteriorate your chances of classifying because they are not good features and they will create like noise-like environment in your classification. It will not be able to classify anymore. So more features does not mean higher accuracy. This is what we call garbage in, garbage out, GIGO. If you have garbage in, you will have garbage out. If you have good data in, you will have good data out. And now we are talking about a single channel. What about 12 channels? What about one application that I'm working on right now, 256 channel high density EEG signals? 256 channels. What neurologist or neuroscientist can visually inspect 256 channels at the same time and give you a certain evaluation or visual assessment of the features that you need to acquire? Who can do this? Let's say you have 1,000 trials for a certain ERP, evoked response, and you have 256 channels and 2,000 subjects. Who can check that? Even your feature engineering will not be able to capture everything, or your feature selection algorithm, because it is very, very complex. What we discovered lately is that you can use deep learning, convolutional neural networks, RNNs, LSTMs, a combination of these, in order to capture features that you cannot see using your naked eyes. You cannot do that. You cannot see them. But when you perform deep neural networks, deep convolutions, deep RNNs, you will be able to capture features just like we do in machine vision. If we are able to detect every minute detail and distinguish, we call this the human level. We all know that machine vision can exceed the human level. It can exceed it. If humans were able to do everything, why would we need artificial intelligence in all cases? In some cases, we don't need it. We just do it for the sake of science. But in a lot of cases, we need machine vision in order to be able to see things that are usually unseen by naked eyes. So this is my take on this. This is why we need deep learning in time series classification. So deep learning for time series classification, or DL for TSC. Let's suppose you have an input, which is a multivariate time series. When we say multivariate, it means we have multiple variables. Multiple variables. How do we look at this? What are the dimensions of this? You need to understand that you have three dimensions. Three dimensions. One dimension is the channels. How many channels do you have? Second dimension is what is your data point itself, so in terms of time. The third dimension that you will have to create is the frame. Okay, so please focus on this. Whenever you are doing a time series classification task, you need to convert or reshape your data into 3D in order to be able to implement conv 2D and so on. How do we do this? Of course, we do not take the whole signal. So you need to start distinguishing between images and signals. Signals might have repetitive patterns and they vary in function of time. In images, we don't have this. In videos, maybe, but in images, we don't have this. So if you don't have a stream of images that is going in real time and the time factor is not important, in signals, it is very crucial. So you need to have the concept of time. However, each sample is by itself an input. So now we are not getting features and feeding the features into the network. We are taking points. Each point by itself will be an input. So we have the point itself in times of t, or in terms of t or n, and we have frames. So we will be segmenting. If you want to see it, to visually see this, what we do is we take this signal and we take a chunk. We call this a segment. And then we take another segment. In order to take another segment, we have two choices. You either do not do overlap. If you work in signal processing, you will know what I'm talking about. So I stop at point number 10. The second segment will start from point 11 and then till 20, and then I start at 21. This is called no overlapping. Or you can take windows that overlap. So I took this window or fragment, and then I take something that overlaps with it. And then I take something that overlaps with it, okay? So it will be a bunch of overlapping windows like this. So this is called overlapping. What we are doing is, we are actually doing something that looks like data augmentation in terms of image. Because in images, you have the luxury to zoom in and consider it as another image, another observation. You have the luxury to crop parts of your picture and consider it as a new image. If you don't have millions of images for a decent deep learning network, what you can do is you can rotate your image, you can crop it, you can zoom in, you can zoom out, you can add some noise, some blur to your image. In signals, what do we do? You might have a question. Okay, so when it's better to use overlapping. Actually, there's like a rule of thumb, okay? So we use a percentage of overlapping, like 25% and 50. I never used no overlap. However, it is the custom. So if you use MATLAB or other programming platforms, you will find that no overlap can be the custom case. However, my advice is to use 50% overlap or at least 20% overlap. This is because we do not want to create any discontinuity between these two, okay? So understand it like this. This information that was over here, I do not want to go over it. I want to have some continuity. So I take a part of it and consider it as a part of the second one. And the third one as a part of the second one. And the fourth as a part of the third one. So you always take like 25, 50% overlap. It will give you a greater results because you will be taking a greater number of fragments. If you think about it, you will have a greater number of fragments. Because if I have a time series and I take a window and then a window just next to it, maybe in 10 windows, I will be finishing my whole series. However, if you do overlapping, you will have a greater number of fragments. You will be going over a part of your data all over again, okay? Therefore, you will have greater accuracy as a result. So thank you for your question. I hope that I'm answering you in a manner that is comprehensible. So that's it. That's what I wanted to tell you about signals. Please keep focusing on these points, take notes of them, because they are crucial to start reading your data, to start pre-processing your data. We have time, we have fragments, and we have this dimension, which is channels. And then we go through the network, which can be a CNN, it can be an RNN, it can be an LSTM, it can be an FCN, which is a fully convolutional network, and it can be a mix. You will be surprised of how much people are trying now to mix networks together and have some empirical results. So without having very strong theoretical justification of why are we using this with that, what we do is we get a convolutional neural network, we add to it an RNN in order to get a sense, let's say, of a repetitive or sequence-like data, because RNNs, as you know, they are used for predictions, for forecasting, they are used for sequence modeling. So since this is a time series, we need the sense of sequence, we need the sense of sequence model and forecasting. However, the surprising thing is, if you go online right now, you find that the issue of DL for TSC is very, very low in terms of papers and in terms of programming work. They all think that, I'm not saying all, most of researchers think that if you use RNNs and LSTMs, you must be using them for NLP or for time series forecasting. How about, or what about time series classification? How do I classify time series? You can use, and you'd better use it to get good results, use RNNs, LSTMs, and so on, and hybrid approaches to classify your time series, as we will be doing during the next part of the session. So please keep this in mind. Let me clear this. Okay, so this is an example of a convolutional neural network. You have your channels, you have times, and you have fragments, okay? So every time you are performing a certain convolution, you are taking a fragment of your signal, but at the same time, you are taking a fragment of all the channels. So keep this in mind now. We are taking fragments of all channels. You have 12 channels of ECG. You will be fragmenting 12 channels at the same time and taking these 12 chunks in real time and considering them as inputs for your neural network or for your deep learning network, okay? So what we will be doing is the following. We will be taking our signals, fragmenting them, and then inputting them into maybe a convolutional neural network, CNN. Okay, so conv2D, conv1D. We will be reshaping our data so that it is valid to be input into such a system. And then we have a layer after a layer until we get to finally to a dense layer. We have the number of outputs, and then we will have our class. In today's workshop, we will be performing a two-class ECG classification system. We will have two diseases or two cardiac anomalies that we will be classifying. So this is an example of a CNN. If you do not have an idea about convolution, let me just draw something so that it becomes clear, okay? So let's suppose you have a signal over here. This is a signal, random, and you have a certain pattern, which is this pattern, a segment. We call this a kernel, K-E-R-N-E-L, kernel. Convolution means I'm going to take this kernel that you see over here and slide it over my signal. Okay, so I take this and I slide it over my signal. Every time I perform the dot product between this kernel and my signal, I will have a certain coefficient. And then I slide it over, I multiply it, get the dot product, and then I will have a certain point, a coefficient, and so on until I finish the signal. So in informal terms, what you are doing is you are scanning your signal. You are performing time scanning of your signal to get the features and the patterns in it. Just like we do in images, we scan X and Y, we have squares, so 3x3 convolution, let's say, and it scans your image up and down. You will be scanning your signals, and since you have multiple channels, your 2D will be this. Every fragment is a dimension, and every time point at a channel will be a dimension, and you will be scanning your signals across all of the dimensions and all of the channels and fragments. This is now an example of what you get if you perform the convolutional neural network. You get a filter. As you can see, this is called the sliding filter or the kernel. You slide it over your signal, which is this, and then we call this the filter response. Okay, so what you see is the filter response out of it. So this is the convolution result. What we are doing is we are sliding a filter on this signal and a filter over this signal. The result of this convolution, as you can see, it's almost identical. So class 1 and class 2, after we slide the filter and perform the dot product over here, we will get almost the same thing. So it does not discriminate any class. And over here, it's almost the same. However, in this region, the result of your dot product will be different. So the dot product of this sliding filter with your class 1 or class 2 will be different. This is where you distinguish your two signals. This is what your convolutional neural network is doing. It is checking at what patterns and at what times and instants you will have distinguished patterns or distinctive patterns that will allow you to discriminate class A from class B from class N. So this is what we are doing in CNN, which is a bit different than the concept of images, because you are used to see it maybe in pixels and voxels if it's a conv 3D and so on. This is an example of an RNN used for time series classification, channels, time, and as I told you, you will have fragments. This is the input series. You will have convolutional layers, and you will have feedback. You will have feedback from a layer to the one before, a feedback from this layer to the one before. This back propagation or feedback that you are seeing over here is the distinctive thing about residual neural networks or RNNs or recurrent neural networks. What happens is you add these residual connections, you perform RNNs, and once you have this, you will have a greater idea about the sequence patterns or the sequence aspect of your signal. Convolution, it gives you a bit of sense of sequence. However, using RNNs is better. And if you wish to have a greater time span in terms of memory, so if you wish to know or to detect or to predict a larger data set in terms of time, so let's say I have 10 seconds, I want to predict 10 seconds, or I have a 10-second fragment that I want to use in order to classify the rest, I need to use even LSTMs. So CNNs get the features, RNNs, LSTMs give you the sequence sense. Okay, they give you this flavor of having a memory in your system. If you have the CNN plus LSTM, and most recently they are using FCNs, which is fully convolutional network. Someone is sharing codes. I don't know why. I don't know why. Please, guys, if you have something to ask, or if you have something to share, let's keep sharing codes and stuff like that till the end. But right now, if you have any questions, just ask them via chat so that we do not waste any time trying to check gibberish messages. But thank you for your question, if it was a question. I don't know, actually. So using CNNs with RNNs with LSTMs, this is as good as it gets. And now they added FCNs to them. So now the state of the art of DLTSC is using LSTM with FCN. LSTM with FCN. This combination is like magic. It works like magic. It won the Physionet challenge. If you don't know Physionet is one of the largest databases of medical signals. It won the Physionet challenge. It won a lot of challenges. If you go to Kaggle now and you see competitions about time series classification, they are using this LSTM FCN. And now they added to it, which is multivariate MV LSTM FCN. And then they added an attention part to it, and it's called attention multivariate LSTM FCN. So AMV LSTM FCN. This is top-notch, state-of-the-art. And luckily for me and you, we will be sharing codes for that and GitHub pages and repos so that you can go and check out the codes yourselves. So I will guide you through the process of downloading data, 12 channels ECG data, and what is the state of the art of this in terms of codes. And I will guide you through the process of doing this alone. So how do I get data? How do I get codes for it? There's an amazing reference that I do not know whether you guys are working with or not. Because a lot of students and a lot of data science enthusiasts and data scientists right now have a problem in getting sample codes. They go to YouTube, they listen to some maybe Indian guys or Chinese guys or Americans giving some lectures. In some cases, it's not very clear. You cannot really understand, and they do not share codes. So you start pausing your video and repeating and writing along, okay? And it might not work, it might be a different version and so on. So what I will be doing is sharing a resource. which is called papers with code. Okay, papers with code. So let's check it together right now before I continue. Okay, so papers with code. Let's go check it right now. Okay, so apparently it doesn't want to go. Okay, that's good. Papers with code. Let's go to it right now. Can you see my screen? The browser, is it clear?
Yes.
Okay, so this is papers with code. If you go over here, this is a very, very interesting and fascinating thing that they've done. I've been into research for more than a decade now. I've never seen such drive and such enthusiasm towards open source data and open source codes. Of course, the GitHub and Git repositories have made this very, very easy. However, now people are like in competitions and in challenges who can share the best codes and have people use them and advance the fields. This was not existent when I used to do research during my first days. We used to hide the codes in like a safe and no one can see it. And if we have a USB over which we have our code, we hide it. We don't want anyone to see it. Right now, it's the complete opposite. You are the best researcher if you care about the domain and you want people to interact with your data. So you publish everything. So please create a GitHub account, learn about Git repositories, go to Kaggle and see the competitions that they are having, the data that they are sharing. If you go to this site, let's go to Papers with Code, the latest with machine learning. Let's say I want to go to ECG classification. It opens. So ECG classification. What you can do using this resource, you can go and check the paper and the code and compare results of all papers and codes. So it's like a review, full review. Let's say I like this method, Physio Challenge 2020. It's a challenge on PhysioNet. Who won it? They won it using 1D-CNN encoder. So you go over here and you press on code. Once you press code, you can go to this guy's GitHub repo. And once you open his or her GitHub repo, you will see the scripts over here. You will see the notebooks. So you have the codes, you have everything. These are all the codes that they used, IPYNB, interactive Python notebook. So you can use this and open it via Google Colab and Jupyter Notebook and so on. So this is an amazing resource actually, that I would love to see you guys use. Okay, I'm going back to the slides. Can you see the slides now?
Yes.
Yes.
Okay. I ask too much, I know, but sometimes Zoom freezes. So I want to make sure that I'm not speaking with myself. So this is what we read, I think. Okay, so this is finally a summarization of the methods that are used for that regard. Multi-layer perceptron, fully convolutional networks, ResNet, encoders, MCNN, LUNET. LUNET is known for images and the machine vision. They created what is called a T-LUNET, which is a time LUNET, MCDCNN, and time CNN. What's the algorithm that has been used? ADAM, which is the optimizer actually, ADA delta, SGD, stochastic gradient descent. Validation train, they are stating over here what is the percentage of test train split and so on. What kind of loss? Does this mean that I have to use these? No, but this is taken from a review paper that I will also be sharing. It's a full review paper, very interesting, that reviews all of the techniques that have been established and used and what are the results that they got. So it's nice to read it before you embark on a certain task. These are the best that they got. Thankfully, we have the Keras tuner. We don't need this. What we can do, as I will be sharing with you as well, a code that I wrote someday, I don't remember when I wrote it, or when I was learning about deep learning and the algorithms. Keras tuners can be used very easily and they are very practical. And you can use them so that you can tune your hyperparameters. This is what we call hypertuning. Because in a lot of cases, and even in research papers, I see people who say, okay, we have a learning rate of 0.01, a batch size of 12, epochs 10, 15, 20, 100. And then when you ask, why did you use this? They say, I think that it's good. I read it in a paper. This is not bad. This is not bad at first. However, if you want to work in a very accurate and efficient manner, you need to be able to answer why 0.01, why not 0.0001. You cannot say that unless you have tried it. Are you going to manually vary each parameter and then go over 1 billion data points or data values? Of course not. Because sometimes every compilation run will take a bit like 20 minutes, 30 minutes if your data is huge. I have seen data sets in EEG and neuroscience that took me about 7.58 hours just to open. Just to be able to open your data, it takes eight hours. To be able to compile something, it takes you maybe 10 to 12 hours. And in Lebanon, I don't need to tell you, we all live here, I guess, or most of us. You don't have electricity for maybe 6 hours, 7 hours. If it comes for about 2 hours, 3 hours, or it comes at night when you are too tired to work. And when your code runs finally and it functions, no errors, electricity cut means you have to run it again, especially on Google Colab. This is why I also advise you guys to use Anaconda, Miniconda, whatever, create environments and have a good PC if you can afford it. I know that the problem is financial in most cases. Get a good PC with a decent GPU and RAM and start working on your local machine. Because using Google Colab is a mess sometimes. You wait 7 hours to load your data, and then when electricity goes away, it vanishes. You have to wait another 7 to 8 hours. Okay, so enough talking or side talking. This is a summary of the architectures that were used. We are not talking about hyperparameters now. Architectures, MLP, FCN, ResNet encoder, the same. However, now they are saying that what are the best architectures that have yielded great results. So the number of layers 4, 0 convolutions, and MLPs, of course. Normalization, no normalization, no pooling, and so on. And you can read about this. Different types of networks. So thank you does not mean I'm leaving yet. I will be running codes. Obviously, it's a workshop. I took a bit of time to explain this. Do you have any theoretical questions before I continue on the actual implementations? No questions. It's either I have good explanation skills or very, very bad explanation skills. All clear. Okay. All clear. Okay, great. I'm glad you are enjoying this. Or maybe you're not. It's clear what you're not enjoying. However, you stayed, so that's a good point. Z. What is Z, Amjad? Okay, that's good. So let's begin. I hope you're ready. Let's download our first ECG dataset. What I'm going to be sharing right now is the following. Okay, so check this out. In order to get your datasets, to get your ECG database, you need to have access to open access data. And since it's open, you have access to it. However, it's kind of a tiring process to go and look for it online, to look for multi-channel or multivariate ECG and so on. So I simplified things for you guys. I made this document just for this workshop. You can use the wget command, or you can use the exclamation, of course, wget, depends. You use it in your Google Colab or on your local machine so that you fetch this data using links. So wget is used to get data via links. Usually it's in a zipped folder, and then you have to extract it. And then after you extract, you import. So you have to understand this. You have 3 phases when you get data. It is called data ETI, which is extract, transform, and import. Okay, so if you're applying for a data science job, you will read about ETI skills. ETI is this. It's being able to extract data from these star or zip folders and so on, because they're huge usually. So we always compress them when we publicly put them online on Drive or GitHub or so on. So it's in a zipped folder. When you download it, you need to extract it. When you extract it, and it requires special libraries, of course, to use Python to extract zipped folders according to the directory that you are placing your data in. So you need to learn about extracting data, unzipping, extracting, transforming your data into readable format or into the format that you wish. It means that, let's say you have a mat file, .mat, you used to work using MATLAB, and now you are switching onto Python. So you want to read a CSV file, or you want to read a mat file and convert it into a NumPy array or a pandas data frame. So you need to be aware of the functions that we use to convert data from .mat into .cs or .csv into NP arrays into PD data frames. Okay, so this is called ETI, extract, transform, import. You use wget to get your data, and then you need to extract it and import it into your workspace. These are dataset links that are more than enough for you guys. If you download these were used for the Chinese competition. It's like a Chinese version of the Physionet competition. Billions, I'm not going to say billions, let's say hundreds of people, hundreds of submissions. You know, in China, you have lots of data scientists, lots of people actually in general. So a lot of contestants. What they did was they downloaded these. So training set 1, 2, 3. You download these. Every file of these 3 is like 1.5 gigabytes. Okay, so the size of each is 1.5 gigabyte. You download them, you open them, and you use them as training data or 80-20 split or so on. Can you please share them here? Yes, I can. So this is the file actually. But it's 1.5 gigabyte, as I told you. So if you want to download it, it will take so much time. However, the data set that I will be working on today is a small data set. It will not yield excellent results because it is small. However, I want you guys to work with me, so I will share the link. So this is why if we got overfitting today, we are getting overfitting on purpose. That's the first time you will hear this. I hope it will be the last time. So I am overfitting on purpose because I do not have the luxury to have you guys download data in super fast manners or ways to be able to open it and compile some high-end algorithms. So, okay, let's share this. I'm going to share links via chat, okay? Let me know if it opens. This is the document in which you find all kinds of databases.
Doctor, we don't have access to it.
We must, doctor.
You don't have access to it. Okay.
When you share the link, you have to give it access, but just.
No, that's great. I think now it will work out. So
Yes.
try it.
Yes, it worked.
Okay, tell me. So this is a resource that is very important. It has dataset links. It has papers with code in which you have the state-of-the-art ECG classification algorithms. So once you click on this, okay, you go to the link, it will open a descriptive page over which you will find all of the current algorithms that are being used for multi-channel classification, multivariate classification for ECG. Okay, so, and the codes are ready. You just have to go to the GitHub repos. If you have a hard time going to the repos by accessing these pages, I already gave you links to the repos. So you just have to go over here and you click on this link. It will take you to the GitHub repo, in which in some cases they have data, in some cases they only have codes, which is fine because they will have a descriptive README file that tells you where to get the data from. So this is MLST, MFCN. This is one of the most important ones, okay? This is the state of the art right now, and you can add A to it with an attention factor. AMLST, MFCN. So this is it. If you wish to download data, and I'll tell you where I download my data from, I went to PhysioBank, which is the archive of PhysioNet. You can see it, right? And you go to the St. Petersburg INCARD 12 lead arrhythmia database, in CardDB. What you can do using this ATM, you can go to the signal, or to the database, St. Petersburg, and then you choose the record. You will have 75 records, I think, yes, 75. You go to the record, let's say L01 or I01, signals all means all of the channels, and then you choose describe record. Describe, it will tell you that this patient has CAD, coronary artery disease, and arterial hypertension. There is some noise in your signal and so on. It gives you the length of your data, how many samples and in terms of time, the sampling frequency, how many points you are taking per second, which is 257, and the number of signals. Let's check it out and see what this signal looks like. So you go to plot waveforms and you go down. Okay, can you see the signals now?
Yes, doctor.
So this is a 12-channel ECG recording. Okay, 12-channel ECG recording. Channel 1, 2, 3. So lead 1, lead 2, lead 3. Augmented VR, augmented VL, augmented VF, and from V1 till V6, as I showed you in my slides previously. So this is one kind of data. Now, can I use one subject that has this disease with another subject that has another disease and consider these as enough data so that we can implement our first deep learning algorithm? Yes, it is. You'll think I'm crazy because I'm saying this. However, you need to understand that the way signals are treated is different than images. I'm not saying it's enough to get good classification. I'm saying it's enough to try out your algorithm and expect something that is better than having one image versus one image. So a cat image and a dog image, and then classifying these two and getting good results. This is crazy. Nobody does it. Usually when we go to deep learning, you should have maybe 20,000 images and plus. In our case, we don't need 20,000 signals because signal itself is divided into time points, into samples, and it is divided into fragments and segments. So each signal is divided into, let's say, n or m number of segments, which will create an augmentation by a factor of m of your data. Is it redundant? No, it's not redundant. Unless you just have one patient, of course. If you have 10 subjects, why am I saying this? Because if you go online now, if you go check deep learning for EEG, neuroscience, let's say computational neuroscience, you will find that most of the researchers have used 10 subject studies or 12 subject studies, which is crazy in terms of images. It's like saying that I have 12 images of tables, or 6 images of tables, 6 images of chairs, and I will be performing deep learning. This will cause you problems, I think. People will not be really trusting your work because it's crazy. Nobody does it. 6 images are not enough. But when we say 6 subjects that have a rare disease and 6 other subjects that have normal heart rhythm, or we call them the controls, each one has 12 channels and recordings for 24 hours, maybe 3 days, 4 days non-stop with a Holter machine, portable ECG. And then you fragment them, you will have millions of points out of 3-4 subjects. So keep this in mind also. When I say keep it in mind, it's not something that I say just to speak. Keep it in mind because it's very important. This point is very important. Do not throw away data because you think that 10 patients are not enough. Do you know how hard it is in the medical field to get data? How hard is it to get EEG of people, let's say, with depression and are willing to let you stick electrodes on their heads? Or people who have a certain disease to let you stick electrodes on their bodies for 2 weeks or a month? Not many people are not many people accept this kind of experimentation. So this is one subject. Let's go to another subject and then start coding. This is LO4 or IO4, whatever. Plot waveforms. Okay, so let's go to 3. I want you to read some other diseases, types of diseases. So this is a signal that has noise. This is, by the way, another challenge. What if we have noise? We have discovered that when you implement deep learning on time series, you don't even have to denoise in most of the cases. It is a bit noise resistant, unlike typical machine learning, where you get your own features. So despite having noise and baseline drift like this, or nonlinear patterns, or nonlinear trends, we call them, you can input this data without having to filter it prior to that. Okay? So let's go to another, that's the last one I'm going to show you, and then we're going to start coding. So this is another one that has a certain trend, okay? Some noise in it. And this is caused by the, we call this movement artifact or electrode displacement artifact. So now that this is clear, what we do is we go over here so that you can use this interface. You go to export signals at CSV or export signals at .mat. It depends what you're using. Obviously, we're using Python for deep learning. We're not using MATLAB. It does not mean that you cannot use MATLAB for deep learning. You can. But I did not see anyone yet in my entourage, let's say, who uses MATLAB for deep learning. I don't know why. Maybe you have more insight. I've never used MATLAB for deep learning. I've used MATLAB extensively for signal processing, for advanced signal processing, advanced signal analysis, basic classification, but deep learning, I never did. So let's say now that I went and got signal 1, which is someone who has, as I told you, if you go to describe record, this guy has coronary artery disease. So what is this in machine learning? It's called our label. This is our label, our class. So this is a patient with CAD. Then we go to subject, we go over here and we say export signals at CSV, as CSV. Okay, give it as text for some reason. Let's take 10 seconds, samples. Okay, so this is it. Samples.csv, okay? Can you see this? Samples.csv. Once you click, it will download this data as CSV. Let's open it now using Excel to have a look at our data before we begin our work. So it will have the label of each channel, lead 1, lead 2, lead 3, AVR, AVL, AVF until V6. This is useless, millivolt, so you delete it. And actually this is useless as well, but you keep it just for the sake of using pandas data frame and taking the labels out of it so that you don't write it again. So you can delete this and you can start working with that. Even the time stamp over here, we don't care about it. We do not care about this. I am not here to get time features and have actual time values. I care about patterns. And if I have samples in order, the signal is in good sequence, I don't care about the actual value. So what do I do now? I create, let's say, a label over here, or let's say cardiac status. Cardiac status. That's an example, okay? I'm going to share with you an Excel sheet, a CSV file. So do not bother to write along. I will share an Excel sheet so that you can check it. So you have this right now. What you do is, we said that this is coronary artery disease. And then we click over here, double click, and you will have the labels set for these signals, okay? It's a big amount of data. Not big in terms of big data, big in terms of the things that you are used to. Okay? Just a second, please. Okay, can you hear me now?
Yes, doctor.
Yes, doctor.
So I took this first subject, and then I'll go to the same website, same page, and I will look for another one. Export as CSV. If you get the description of the second one as well, you will check the case that they have. So coronary artery disease, what we do is we go to export as CSV, and then we take this samples. And once you take this, I know what you are thinking right now. Are you actually going to take hundreds of patients right now in front of us and concatenate? No, I'm not. Okay, I'm just showing you how to manually do things if you want to test out a few concepts. However, usually we have signals that are automatically created if we're talking about offline analyses. Okay, we have databases, online databases. You can use special database functions, SQL, and so on to create such tables and to be able to get them concatenated and input in your system. However, in my case or in your case, I'm trying to be as basic as it gets so that everything is clear. Even the database formation part, I want you guys to get a glimpse of it. Okay, so this is the goal. The goal is not to actually waste your time concatenating vertically. So now I took these signals. What I do is I open the new signal data set. Then I delete these. Okay, I delete them. I don't care about them anymore. Then I write CAD as well over here because same disease. And then Control A, copy. And then I go to the second, the first one, which is that. I go to the end of it. And then you can go over here and paste them. You will say, what is this structure? Thousands of points, then 0, 1. I told you, we don't care about the actual value. We will end up dropping out this column from the data frame. So now, this is the actual thing that we do. All of these are CAD. Now what we do is, I will not do it. I will share the Excel file directly. We will have other types of diseases that will go under these, and we will change the label. Okay, so we change the label, and then we will have 2 labels, 3 labels. In our case, we will be doing binary classification, 2 diseases because of time constraints. In your case, you can have fun with this data set. It has like 6 or 7 diseases or anomalies. You can download everything, concatenate, figure out a way to download them and concatenate them automatically, and then start performing what you want to perform. So now I'm going to take you to the actual file that I created for you guys. Okay, so I think that I placed it in this folder. This is it, ECG 12 channel database.csv. Okay, so share, and I will send the link via oh. Please tell me if you can open this.
Yes, we can.
Okay, so if you open this file now, you will have 2 kinds of diseases. What can you see in the label section? Or do you want me to open it? I can open it now. You will have the sample. Sarah, you were asking what kind of timestamp or index do we use? It doesn't matter. We are going to delete it anyway. It doesn't matter. So you can keep the time in terms of date, month, day, year, so on. You can keep it as number of samples. You can keep it as milliseconds, seconds. It doesn't matter. You're going to, okay, so AMI and CAD, coronary artery disease and acute myocardial infarction. These are the two diseases that we have data for, okay? So going back now, let's go to the code. Let's go to the code now and start coding. If you have this file, you need to open a new Colab. I don't know if you guys have all worked with Colab. If you have Google Drive or Google accounts, all you have to do is write Colab or Colab Research. It should open up. If you have a Google Drive, it will automatically open. So if you're using Chrome, you're already logged in. You just have to write Colab and it opens. In your Colab, you will be able to write codes. You will be able to run them, write text, titles, and so on. And you can even upload files.
Can you please share the code also?
Yes, of course. Of course, I can share it. Saved. I think I downloaded this. I'm gonna re-download it now. Okay. So this is the code now. Kindly let me know if it works. You should be able to access it via Colab. Can you access it?
Download.
It's downloading?
Yes,
Okay, okay.
can access.
You
في
can
من
access.
تحت you can access it directly from Google Colab. في من تحت icon Colab automatically it redirects to Google Colab.
Do you have any technical problems or is it okay? What you can do is you can open Colab, okay? If you have your Colab now open, you do this Colab file and open notebook, okay? File, open notebook. So let's say I want to open this. In my case, I go over here, I upload, choose file, okay? Choose file, and then I choose this and open. Okay, guys, is it clear now? So it's easy to open, not a big deal.
Doctor, just I have one question, sorry. When you export the data to CSV file,
Yes.
how can we know the number of the Excel's line generated by one diagram?
The
Is
number
there
of
any rule? Lines in Excel for one exported.
you mean the number of points, number of samples?
Exactly. Can we know this? Or
Yes, of course, it's over here. If you go to this describe record, okay, it will tell you how many points you have and at which sampling frequency. So if it's at 257 hertz, so you will have 257 points per second, right?
Okay.
And you have the length. So and over here it says 426,600 sample intervals. You can multiply this by the number of seconds and you will have it across 12 channels, and you can take this number, okay?
Okay, very clear. Thank you.
Let's go towards the first step. If you are following along, I've already implemented this. So I'll not be rerunning the code. I will be explaining the code and telling you step by step what's happening. So step one, of course, in all coding, whether it were C or FPGA programming or using HDL or Java, whatever, any kind of programming language, of course, including Python, you have the same structure. The structure begins with importing packages, importing libraries. So now we need to import libraries. What are the libraries or packages that we need? We need TensorFlow because we are using TensorFlow. Of course, it is not the only one. You have TensorFlow, you have PyTorch, you have Caffe, you have a lot of frameworks that you can use in order to perform deep learning. However, there is like a debate on which one is better. And you cannot give a clear answer because it depends. It depends if it's in terms of open source level, how open source is it? So how accessible are the codes? How difficult are the implementations and so on. You might be maybe comfortable using PyTorch rather than TensorFlow, and you might be comfortable using TensorFlow and not PyTorch. So it's up to you. However, by experience, I see that TensorFlow, even if you go towards certifications and so on, you can get certified, you can perform international exams. It is sponsored by Google eventually, so it is something that you would want to have on your CV if you're in your starting phase of the career. You would be surprised to read how much people are asking for TensorFlow expertise in data science now. So just go to LinkedIn and turn on alerts for jobs and write TensorFlow in your search terms, in your filters. Turn it on and leave it. The second day, you will have 40 alerts. Third day, 80 alerts. Every day, there are 40, 35 openings worldwide for people who have expertise in deep learning and especially in TensorFlow. And if you get certified, you can go now for $100, write on Google, certified TensorFlow developer, okay? And there's a course given by Lawrence Moroney, who is a Google AI advocate. So if you study the course and you go through the material, you will have enough experience to go and go through the test. If you are certified by Google, you will be certified for 3 years, and it is very helpful in your career. Because it's a way to say that, although I took an online course for it, it's not from Yale or, I don't know, I'm not going to say Yale engineering, we don't really talk about Yale. Let's say MIT, Stanford, Carnegie Mellon. It's not from a prestigious university. However, I am certified by Google, which is some way of authentication of your skills. So import TensorFlow STF, and then you will have some sub-modules of it. So TensorFlow Keras, TensorFlow Keras layers, and TensorFlow Keras optimizers. So sequential, in order to use sequential neural networks, okay, to be able to start and building your layers. This is the basic architecture that allows you to start building layers. Then layers, what kind of layers do you want? Flatten, dense, dropout, batch normalization, conv2D, and max pool 2D. I don't want to go into all of the details. I advise you guys to go to Coursera and study the deep learning specialization by Andrew Ng, okay? The deep learning specialization by Andrew Ng is one of the most beneficial things that you might study, maybe in the intersemester break or so on. And if you get certified, it's fine, but it's not something that is very official. He is a professor at Stanford, and he is the founder of DeepMind, and he's an expert in this field. Then you import pandas to get data frames, which is a way to see your data in a good format in terms of columns and rows and headers and titles and labels. It's a very nice way to access dictionaries and to access data sets. Import NumPy for numerical analysis, NumPy to create data arrays, to be able to compute numerical analysis, numerical operations on arrays. So anytime you wish to perform mathematical operations, you need NumPy. Every time you have a data set, a dictionary, you need to use pandas. And then in order to draw, you can use matplotlib, and even a better version of matplotlib is Seaborn. Okay, Seaborn. If you want to know how to write it, it's Seaborn. Seaborn is a very nice way to plot your, to be aesthetically advanced in terms of colors and in terms of graphics. Then from sklearn, scikit-learn, this is used for machine learning, of course. Scikit-learn model selection, you import train test split. This is how you can take your data, you can set what is the percentage of training. Now let me tell you something about training that you need to be aware of. If you are talking about hundreds of data sets or points or thousands, you would better take 80% for training and 20% for testing. However, if your data is huge, let's say millions of points, millions of images, the advice is to use 96%, 98% for training and use the rest or the remaining 2% for testing. Because the 2% that you think is little is actually maybe 1 million images if you are talking about billions. So 1 million is enough. So there is no rule of thumb concerning test split or train test split. They always say 20 80 75 80 20 75 25 70 30. But if you want my opinion, it depends on the amount of data that you have. If it's huge, you can go even further. Train it more and then have your testing over the remaining 2 or 3%. Once you run this, it should run. It should import everything. Okay. It will load depending on the connection, depending on what kinds of libraries you are downloading. If in case you try to import and it doesn't function, go for pip install. Okay. So let's say I have something that does not get installed like this. You just go for pip install. And then you state whatever you want to install. It will install it. So instead of importing it, you install it. This is a tip that is useful sometimes. You might not be able to do this all of the time. And even if you have multiple libraries, there's something that is nice, which is create a notepad inside your note, call this notepad requirements. Okay, so text file, requirements, and take this. Let me see if I have one. Requirements. Requirements. Okay, check this out. Do you see this? The notepad, can you see it?
Yes, doctor.
Yes, doctor.
Okay, so if you have multiple libraries that you want to download and you do not want to go over it, import, download, what you can do is the following. You can create a note file or notepad. You can write whatever you want to install and equal to state the version. And then once you save it, what you do is you place it over here, you upload it. So upload to session storage. You place it over here and then you just write pip install requirements. Okay.
It's
Pip
like
install.
it's like when you deploy to Docker, you do the same, right?
Yeah, exactly. Yeah. So this is easier. I'm trying to give you things that will simplify work. Instead of writing them every time, you can just download it as a text file and import them automatically. Then you have the ETA, which is the extract, transform, import. You already have the file. If I want to open it, it's not over here, okay? It's not over here. If I want to open it, I need to go to upload or I need to load it. We have functions to load. In my case, I can load it manually. So I can go to the folder. I created a folder for this. And then I will have this file and open. Okay. In your case, let's say you took my file now via drive and you saved it over your drive. Let's say you want to open huge amounts of data. Is it logical to go every time and manually upload it? Of course not. What you do is this. You mount your drive. What this means is once I click on mount drive, everything in my Google Drive will be accessible from this platform, from this runtime. So now I can just mount my drive and everything in my drive will be over here under drive, and you open it and you can have access to all of your data. Okay, so now you have two options to follow with me. You can either do this, which is easier, and you can mount your drive if your data is on the drive. Else, this will not open. It will say, I do not have data. There's nothing called ECG 12 channel. So now what we do is we take our data, which is a CSV file. Okay, I'm gonna zoom in a bit. I take my database.csv. You can use double quotation or single, same thing. And then you write the name of it, .csv with the extension. PD, which is for pandas. How do you know this? It's over here. Import pandas as PD. By the way, you can just write import pandas without as PD, but if you want to use functions that belong to this class, you need to write pandas. So to make things easier, we name them PD. We have objects now, PD, NP, PLT. It's easier, but it's not mandatory. So PD dot read CSV. So now we are going to read a CSV file, which is ours, and we are going to print, which is to get the output, data.head. When we say head in Python, it means typically we have the first 5 values. So the custom is 5 values. If you wish to have more, you can just vary this number. Instead of saying data head and leaving it open, you can write 100. If you write 100, you will have 100 values. Okay? Data.info. So now let's see, print data.head, what we got. We got the first 5 rows with all columns, and of course it will give you 3 points over here, etc. It means that it has a lot of channels that will not be visible over here. So they show you the first 4 and the last 4, or 5 in this case. I have the label, CAD, CAD, CAD. I have time series for all subjects, channel 1, channel 2, channel 3, or lead 1, lead 2, lead 3, AVR, AVL, AVF, V1, V2, V3, V4, V5, V6. So this is my entire data. It's 5 rows that are showing, of course, and 14 columns. Data.info, it gives you information about your data. Okay? So what kind of information? If I have certain classes or columns, I will have the titles of my columns, and each column, what type of elements it has in it, floating numbers, integers, strings, whatever, and how many non-null value there are. Okay, how many non-null values you have in your data set. So these are all float 64-bit. This is an integer, which we will neglect, we will erase later on. And this is the label, which is an object. So this is data info. Data shape, if you use data.shape without opening this, it's an attribute. Data.shape, you will have the actual shape of your data, which is 15,420 points. These are rows, which are the samples, number of samples. And this is 14, which is the number of channels, plus the sample column, plus the label column. Okay, is it clear? So 12 channels, sample, label, these are 14. Now, let's get the data distribution. This is very important if you want to study the fairness of your system. What do I mean by fairness? Let's suppose that you are working on a certain cat versus dog, let's say, application. This is very famous, so we always give examples about this. It's easy to understand. If you focus on special types of cats, they are cats. We did not say that they are not cats. If you focus on a certain type of cats or a certain breed or something, and then you give, let's say, 90% of a certain type and 10% for the other types, your system will not be fair. Actually, it will be biased towards the highest percentage of classes. So 90% of the cats are, let's say, black cats. And then you have for blonde cats, let's say, or white cats, the remaining 10%. 10%. This is not fair. Is it correct to do? It's correct. However, it is unfair and it is biased. because you are training most of your system's capabilities and power onto the 90% or 90% of a certain class. And when an image of a white cat does appear, you cannot classify it with credibility as much as you can for others. So this is why we get the data distribution. So I go for data, which is a data frame. I open my brace over here and write label. So this means get me the column entitled label, okay? The column that is label, and get the data in it. However, I have dot, so there's another function then. The other function is value counts. So let's count the values of each label. Okay, do you get this? Now we do this to see how well distributed is my data, how equally distributed. So I have two diseases, CAD and AMI. Are these two equally distributed? Or maybe I have 10 million points of AMI and 10,000 of CAD. We cannot have this. If we have this, you have to have a certain compromise. You either have to truncate the additional part of AMI so that it's equal to CAD, or go look for some CAD patients and get their data. However, having unbalanced data is not good. So data label value counts, we have 7710, 7710, which is equal, and I made it on purpose actually. I took 3 subjects of this section and 3 subjects of that section, and I got this, 7710, 7710. Now, data information, what's the information of my data? We already saw it, we already saw this, so this is it. Non-null values, this is the amount of data samples, and this is the type. Now we go for setting the sampling frequency. What is a sampling process, and what is the sampling frequency? If you have a signal, this signal is usually continuous before it enters any device. Once it enters your device, let's say it's a microcontroller or a PC or data acquisition system, automatically as step 1, you need to perform analog to digital conversion, ADC. Once you perform ADC, it becomes digital, it becomes discrete. What I mean by discrete is the following. This is my data. It was like that. What I do is the following. I take samples, sample 1, sample 2, sample 3, sample 4, sample 5, at equal intervals. This is typically at equal intervals. So this is called sampling time. Between the sample and the other, it's called TS, sampling time. And 1 over TS is your sampling frequency, FS, or sampling rate. So when I say 257, I mean that every second I will be sampling 257 data points. Okay? So keep this in mind. Now, after I set this, I need to create classes as the indices of data labels. What I mean by this, I want to classify, so I need to create classes. What are my classes? My classes are either AMI or CAD. So what I write is the following. Classes equals data label value counts, just like we did over here. We take the value counts. However, what we do is we add another function. This is amazing about Python, actually. You cannot do this compound functions in other languages, at least not in C. So data label dot value count dot index. So it's like one line of code that has 3 different functions. You access the data in a label, you got the value counts, and then you got the indices of these. And then you print them. What they did was they scanned whatever is in your label and has counts, and then they took the indices. So you will have the AMI, acute myocardial infarction class, and CAD, which is the coronary artery disease. Now, what are the columns? I just wrote these just in order to expose these functions, to show you these functions, okay? So just for that purpose. You don't have to do all of this. You need to know the distribution. You need to set the sampling rate, but having this printed every time is not necessary. It's unnecessary. Data.columns. So I am getting the columns of this data frame. You will have sample 1, 2, 3 until label. Now let's plot. One of the things that I do not like is when someone always writes code without functions. This is not good practice in programming, because in all cases, you will need to plot data. In all cases, you will need to import data. In all cases, you need to tune your hyperparameters. In all cases, you need to stop at a certain accuracy. In all cases, you need to perform some kind of label encoding. So why do you always write it and copy paste? Why not create functions and then have your data as inputs to these functions? So you just have to call the function instead of always writing the code all over again. This is good programming practice. So even plotting, if you have multi-channel data, use my code over here as a reference for you, okay? Define, which is a function, plot class, so plot for each class, which has arguments, the inputs are data and label. Now we create a figure. AX0, using AX in PyPlot is a way of creating functions with graphs, okay? So AX is like a graph object. So if you have 3 channels, you use AX0, AX1, AX2. If you have 5 until AX4, I have 12, so until AX11. So AX0 until 11, plt.subplots. If you work with MATLAB, you know what subplot is. Subplot means I have graph of channel 1. I drew it over here. I do not want to overlay. I do not want to overlay signals. I do not want to do this because firstly, it will create some kind of maybe blurriness or some kind of maybe unclear view of my signals. And the most important reason not to use this is the fact that you are abiding now by or bounded by the same scale, Y scale. So if one signal has a pattern but greater amplitude than the other one will show as a 0 signal because it does not appear with respect to the other one. In our case, this is the case. Not all leads will have the same strength in terms of millivolts amplitude. So what we do is we draw others. We draw another subplot, a third subplot, a fourth in terms of rows, and you can also do it in terms of columns. Okay, so this is called subplotting. Row 1, row 2, row 3, column 1, column 2. Now, PLT subplots, number of rows is 12. When I say this, I'm saying that I want to see 12 ECG signals, one under the other. So straight under each other. Fig size equals 15.7. I am choosing the size of my figure. So in the same function, same line, you can do everything. Share X equals true. It means that they all have the same timestamp. And this is well known because you are recording simultaneously. You are recording 12 channels at the same time. So why have different axes? You will have the same X every time. So plot axis AX0 data sample, data 1, lead 1. It means that use this element to create the first graph, which is data sample, which is X, and this is Y. So this is the graph object. This is X, this is Y. And this is what we will call it. We will call it lead 1. The second one will have sample. It will be column 2, which is lead 2. And then we will call it lead 2, and so on until we reach this. And then the height space between each plot and the other will be 0.2. So PLT subplots adjust each space. And then Fig subtitle, it's not a typo, sub yani superior. It's above it. So subtitle, label, PLT subplots adjust. So these are all configurations that you can check. PLT show. PLT show is the one that aids in the showing the figure. Until you write PLT show, you will see nothing. And then plot axis. Now I am defining the axis that I am plotting. So let's take AX. It will have X, Y, and a title. So this helps in configuring the axes. AX.plot XY. So it will have inputs X, input Y. And this is G. So of course, you can go to documentation of PyPlot and check these because I want to focus more on the machine learning algorithm. We still have 25 minutes. So I do not want to waste your time talking about plots. And then you do not want to set it as visible, the X-axis. You set the limits for y and the limits for x, which is minimum till maximum. And over here, what we're doing is normalizing. We are taking the value and subtracting the standard deviation. This is called normalization. So what we do is we take minus standard deviation plus standard deviation so that you are centering your signal. And then you show the grid. And finally, for label in classes, plot for each label its data. How much data are we plotting? It's fs times 10. So from 0 till fs times 10. In our case, fs sampling rate is 257 times 10. You will have this much points. So every time you need to plot and see nice looking graphs, you can take my function and use it. These three together. This is an example of an AMI patient's data, and this is an example of a CAD patient's data. So AMI, this is channel 1 or lead 1, 2, 3, AVR, AVL, AVF, V1, V2, V3 until V6. As you can see, they differ. They only coincide and are synchronized in terms of the R peak, which is the heartbeat of highest amplitude. So this is a sample of the AMI signals. If you look at the CAD, this is a sample. They might seem as if they were the same, but they're not the same. They have different amplitudes and slightly different patterns. If you look closely, this is different than that. It has same phases and so on, but it's different. Okay, so this is an example of the data. Now, if I ask you, can you visually tell me what features differentiate this CAD from this? Of course, you will say no. You might say, well, I can see that you will have a valley over here, and over here there are some oscillations. Yes, this is informal talking. How will you get this in terms of numerically? Numerically, how will you get this? How will you describe this in terms of actual parameters, actual features? You cannot. You cannot. You will have to do trial and error unless you are an expert in this. And even if you are an expert, you will not be you will not have greater expertise than a cardiologist. And deep learning has proven to beat cardiologists in this. So this is AMI, and this is CAD. An example of each. Okay. Now we pre-process our data. Just like I told you, what we want to do now is use the capabilities of data frames and the features of data frames to clean our data. What do I mean by cleaning? I want to drop the sample in this index column, sample indices. I do not want them. Why would I want the samples? Sample 0, sample 1, sample 2. And then when I get to the other subject, it will repeat. It will go back from 0. I will gain nothing from it. So what we should do is we should drop this sample in our case. So we drop this column by using the data.drop, which is the data frame.drop. So if it's called data, you say data.drop. If you call it maybe FF, it will be FF.drop. And you are going like this horizontally, so axis equals 1, and you drop the first one, which is sample, and then dot copy. So now what I did was, in order not to mess, this is very important by the way, in order not to mess with my data set, I do not take the data set and drop columns from it, because I might need that column later. What I do is I take this, I perform a copy, I create a copy of it, and then I call it otherwise. So now I have a copy with a dropped column, and I call it ECG. Then I'm using head 100. As I told you, head usually gives us 5. Now it's giving us 100. But of course, it will not show you 100. It will create these points. So 0 till 4, and then first 5, last 5. Now what we have is good, decent data, decent looking data for machine learning. For deep learning, you have the channels, and then you will have your labels. Now, ECG label value counts. I'm going to count my values as I told you previously. What's the shape? The shape is row times column. I will have 13 columns are not 14 because the index 1 has been deleted. And I will have the number of rows, which is the number of data points. Then you all know this. If we have some labels that are categorical, yes, no, true, false, white, red, black, this is not something that you can input into a machine learning algorithm and understand. You need to have numbers. So you either do one-hot encoding, which is if you have multiple categories or classes, it will be 0, 0, 1, 0, 1, 0, 1, 0, 0, and so on. It's like binarization. And you can do what I did over here, which is using the label encoder. So you write label equals label encoder. Now you instantiate this. We call this instantiation. Once you instantiate it, you can use it over here by using the fit transform function. So step 1 is instantiate. Step 2 is fit a transform. So you take your labels and you fit the transform to what? To the label column of your data. So I create and instantiate an encoder that will give me numbers 1, 2, 3, 4, 5, 6, and so on. And then I fit it to my data. Now it looks like this. My previous label was CAD. My new label is 1. Now if I write label.classes underscore, I will have AMI and CAD. Now there's a very important point that a lot of people do not do, which is standardization. Standardization. If you have data of multiple channels, you want to have the same variance. You want to have the same variance so that when this kind of amplitude data goes into your network, it focuses on the pattern rather than focusing on the value itself. Imagine if lead 1 has a value of 50, 60 millivolts as a peak and V1 has 10 millivolts. I care about the pattern. I don't care about the value. I want to see how it behaves electrically in terms of pattern. So why saturate it with high values and make it believe that the value is very important? Do you have a question? Someone open the mic? No? Okay. So I'm trying to go a bit faster. I hope that the administration can give me like 5 minutes extra. Can we do this? Can we have 5 extra minutes?
Yeah, sure.
Okay, thank you. So the thing is, we don't want to focus on the amplitude. We want to focus on the pattern. So what we do is we create X, Y. X will be the actual channels from 1 till V6, and Y will be your label, just like we do in all. Okay, what happened? Okay, so scalar equals standard scalar. What standard scalar does is it scales your data, it performs normalization. How do we normalize? It's something related to statistics and mathematics. You can read about it. You can either subtract the mean, or you can divide by the standard deviation, or you can do both. You subtract the mean and you divide by the standard deviation, you will get what we call the z-score. Okay, how far is it in terms of standard deviation numbers? So this is an important point to realize, which is you need to scale your data. So you instantiate the scalar, just like you instantiated over here the encoder. When you open the parentheses and leave them blank, it's called instantiation. I'm having a hard time pronouncing it. So scalar is equal to standard scalar. X equals scalar dot fit transform of X. So you apply this to your data, which is X, your channels. Previously, we did label encoding on the labels. Now we do scaling on the data, so on X. Then scaled X will be a new data frame. So now how do we create a data frame? Previously, what we did was the following. We imported our data as CSV, okay? So automatically we did pd.csv read. So it created our data frame. Over here, no, we have data. We want to create a data frame out of this data. We're not doing this in a single function. So what you do is pd, which is pandas.data frame, and then you state your x's and your y's. Okay, so be aware of this. In terms of pandas, you either read your data as pandas data frame to begin with, just like we did with our ECG signals, or you can create your own if you have an NumPy array or if you have a certain array of data. Scaled X is pd.data frame. What is my data? It's X. What are the columns? The channels. And then scaled X label equals Y values. Now I will have my X, which is the channel data, and then Y will be my labels, my classes, which is AMI and CAD. Now, what does it look like? It looks like this. This is my data right now. It is all scaled. It is all standardized, and the labels are numeric. So now we can say that we are good to go in terms of machine learning. Now, what's the difference between time series classification and between working with images? With images, you don't really fragment the images unless you have a certain purpose for it. With signals, we never take the overall view of the signal. We need to fragment it, firstly, to augment our data. Secondly, to be able to have high dimensional data for our convolutional neural network and other neural networks. So what we do is we import scipy.stats, which is a part of scipy or module that helps us perform statistics. And then we need to divide our data into frames having hops. I already explained this, remember? I told you that you had your signal, and then you divide it into frames. And if you want to have overlap, who can tell me what's the overlap over here? What's the percentage of overlap over here?
50%.
Yeah, exactly.
25 to 50.
No, over here it's 50. Because
50.
because you have 80 samples in terms of frame size, but the hop is 40. So my fragment is 80, but I hopped 40. So I still have 40 to go. So there is 50% remaining that that will intersect with the second one. Now, when I set them in terms of my sampling frequency. This is also a rule. Because if you know the sampling frequency and you know how many seconds you want in terms of fragments, it's easy. I know that I have 257 points per second. If I multiply by 4, I will know how much it will be in time. However, if it is a certain number that you randomly choose, it might be very high, it might be very low. If it's a function of fs, it's easier to understand. Then there's this function. Yes, go ahead.
Doctor, sorry, I have a question concerning when having imbalance data set in the time series data. Is the balance technique useful in such a case or not?
Yes,
like,
of course.
Okay.
Of course it is. In my case, I took them to be equal so that I do not take too much time in explaining the balancing issue. However, it is very, very important because if you have certain patterns that you focused on and the rest is not really taken into consideration, you will be overfitting towards and biasing your system towards the patterns that you took. However, if you give it a certain type of signals that is of the lower percentage, it might not recognize it as much.
Okay, so we can use technique like SMOT in such data series problem.
Yes.
Okay,
Yes,
thank you.
Of course. Okay, so now I will be also sharing this function in the code. You can use it in all kinds of data. You just have to manipulate this depending on the number of channels. This is define get frames. So this is the frame fragmentation or segmentation of your data. Any data frame, okay, any data frame df that you have, if you have a frame size and the hop size that you set over here, you can fragment your data and convert it into fragments. So take segments out of it. Number of features is the number of channels that you have. Each channel is called feature. It's not like features in the typical sense, which is amplitude, frequency, and so on. This is number of features is the number of actual channels. And then you open an empty array, which is, or an empty list frames, and an empty one, which is labels. Frames and labels, it will get filled progressively. Now, for I in range, which is our way of saying for I from this point to this point, for I in range 0, length df, length of df is the actual length of your whole data set, minus frame size, hop size. So you are going in hops from 0 till the length of the whole signal minus 1 frame. So this is what you are doing, because finally you will not have any frames. It will always miss 1. And you have 0 over here, so you have to subtract 1. So 0 in hops until you reach the whole length minus frame size. And now you start creating your fragments. your fragments for each channel will be defined separately. So for the first fragments of the first channel, DFI, which is or 1, lead 1, values from I, which will begin with 0, till I plus frame size. So if your frame size is 10 points, from 0 till 10, and then when you go, it will be from 10 till 20, and then from 20 till 30, 30 till 40, 40 till 50. This is what we're doing actually. We are segmenting in frame size segments and then saving them into A, B, C, D, E, F, G, H, G, and until M. Of course, I did not use I over here on purpose, H, J, K, L. So I did not use I for a certain reason because I am using I as index. So be careful about this. Do not use a letter that is being used because it will generate errors. Now what happens is the following. Focus on this point. Let's say I'm taking fragments of our data. Okay, so let me write this. Let's say I am taking fragments. I took the first point, second point, third point. They are all CAD now. Okay, so all of these are CAD. And then I will have, what's the name of the second one? Who remembers? AMI, right? So AMI. Let's suppose that my fragment started over here and then it stopped here. Is this a problem or not? Aren't you taking fragments that are supposed to be in the same class?
Yes, it's a problem. We have to take in the same class. It will be overlapped like this.
Okay,
and
so
we miss.
What's the solution?
The solution taking each class.
Okay.
Taking each class, taking each class and separate the data by segment to not fall into this problem.
This is one solution. It's inefficient, but
Can we subtract the overlapping part?
So you need to check if there is overlapping and not subtract it.
Yeah, divided by 2, we can, yes.
You're losing data now. Now you're losing data because you took the points that belong to the data set and you removed them. The smart solution that we usually do is to get the class in this fragment that is mostly present. So what do I mean by this? I mean that over here, I'm taking stats.mode. What is the mode in statistics? It's the value that is mostly present, right?
Most frequent.
Okay, most frequent point or mostly present. So if I have a fragment in which I have 2,000 points that belong to CAD and 3 points that belong to AMI, I can say that I will consider these 3 points as CAD. Okay.
Oh, nice. So yes.
I will group them into CAD because it's like an outlier in this case. So I can consider it as being inside the data. Is it better to delete it? I think it is better so that we do not interfere with our data and consider data that is AMI, which is actually not AMI, let's say. But it's done usually because we have a small, very, very small amount of outliers. So it will not affect our results. But you can always find smarter ways to do it. This is the way we do it. We do stats.mode. So we check which is the most frequent class in this fragment. If it's CAD or class 1, we will consider it to be the label for all. So it's like you are restructuring your labels or reassigning labels for these points that lie on the intersection of these fragments. This is what we did. We took stats mode. Let's say it said that class 1 is the most frequent. I'm going to append labels.append label. So I'm going to take this label, which is the new one, label CAD, and append it to this, and it will all be now CAD. So this is how we do it. It's a bit weird. However, I think it's a smart idea to work around it. Then bring the segments into a better shape. We need to have a certain shape for our segments. There is a typical shape for the convolutional neural network, which is this. Frames is an array that is a reshaped version of your frames that you got. Who knows what -1 is?
From the last.
Okay. Last or first? Last, right?
Last, I think.
Okay. So what we do is we reshape it into frame size and number of features. This is typical, so don't go really deeply into this. It's very easy. It's just a matter of restructuring, reshaping your data. This is your frame now. You will have a number of frames, and your labels will be an array. You create an array because it was a data frame. Now you need to create an array to be able to perform the machine learning. So NP as array labels, and then you return, which is the output of your function, frames and labels. Now what we do is we create X, capital X and lowercase y, get frames, which is this function, get frames. You are calling the function, and it will give you scale, so it will implement it over scaled X with frame size, set, and hop size. It will give you the frames and the labels for them. And then we will print the shape, which is x.shape, y.shape. You will have 28 by 1028. So it will be a number of fragments, let's say 28 fragments of 1028 points, or the opposite, depends on how you place it. And 12 will be the number of channels. Okay, so this is the shape of X. The shape of Y will be 28 and empty over here, which means that it will be a column vector of 28, which is 28 labels. So we will have 28 data sets of, or fragments of 1028 points. Each will be assigned AY, which is the label. Now this is the famous train test split, which is X train, X test, Y train, Y test equals train test split. You divide the frames that you get into test and training. What we did over here, because the data size is low, we did 0.8 by 0.2, which is 80% training, 20% test. And then we print the shape of X train and the shape of X test. This is important to get now. Okay, we've reached the 2-hour limit. Bear with me just 5 to 10 more minutes, please, so that we can finalize the code. I apologize if I bored you or if I bothered you with so much speaking or information. However, I hope that it's useful. So print xtrain.shape and xtest.shape. We got the shapes of them. 22 by 1028 by 12, which is known. And then train 0 shape, we are checking what is the size of each training data set, which is 1028 points for 12 channels. Now we reshape it to 3D to be acceptable as CNN input. Why am I saying this? Usually when you have a certain image, how do you interpret images? Images are actually X, Y, right? So like this. And if it's a color image, what will it have? It will have 3 fields, right?
3D, 3 channels.
Yeah, which is RGB.
Yes.
So RGB, and you will have the pixels and the values. So it is 3D actually. You will have 3 dimensions, the X and the Y and the RGB channels. In order for the convolutional neural network or any other network to function, we need to reshape our data. How do we reshape it? We just add 1 dimension over here. What are these numbers? Where do I get them from? I get them from this. So you always have to get the shape of your training data and your test data. Once you get them, you take these numbers and you add 1 dimension to them. Is it clear? You take the size and you add 1 dimension so that it is 3D. So 22, 10, 28, 12, 1, you add 1 dimension to it, and you reshape also your test to have this added dimension. Now, what is the CNN model? In this case, so that I do not overcomplicate things, I implemented one of the most basic time series classification algorithms, and the rest is a surprise. I gave it to you as a code. You can open it and see how accurate it is. And if you have any questions, you can always email me, okay? If you wish to write my email, I don't know if it's written somewhere. It is this, sorry about the pink color. I did not mean to use it, so it comes like naturally. So this is my email, ramzi.o.halabi@gmail.com. Okay, this is my email. So if you have any inquiries, you want to ask me about data sets, you want to ask me about some codes, if you want some resources, some help, I would be glad to help whenever I have time. Okay, so now let's go and finalize this. This is our model. we create model equals tf.keras.models sequential. This is the way to start a deep neural network. Then tf keras.layers, which is something that we imported previously, layers of keras. We start with a convolutional layer having 16 filters of 2 by 2. Okay, 16 filters of 2 by 2. Activation is rectified linear unit, which is ReLU. And you have leaky ReLU and stuff like that. You can read about them. As I told you, if you follow the course of Andrew, you will have fun. Input shape xtrain 0.shape. So what is the shape of my input? I need to take the first dimension of my training data. This is how we do it in signals. Xtrain 0.shape. Then you create a dropout layer. What is dropout? Dropout means usually what I have is neurons.
To reduce the number of neurons.
Yeah, exactly. And every neuron is connected to every neuron, right? Fully connected. This is typical. This is typical in neural networks. What if some of this connection is not important? What if it does not lead to accurate results or good results? What if it is lowering my accuracy? What if it is adding some useless information? What if it is adding parameters to my network? Imagine if we can drop out 10% of these neural connections. And if we go right now, if you check this, okay, let us check this first. This is model.summary, the model that we did. You already have 1,456,434 parameters in your network in terms of biases and weights and so on. So if you can drop 10%, 20%, you are really releasing some space and some computational power. And especially if you wish to use this for deployment. I don't think we'll have time to discuss deployment. However, please, if you have any inquiry, as I told you, we can have Zoom meetings, we can have Teams meetings. It's not just related to this workshop. I would love to meet you all. And if you have questions, if you want to work on some common projects, if I have time, I'd be more than glad to do so. So deployment will not be covered, but I can share with you some PDFs or something if you send me an email. So now let's go over here. What we did is drop out. What is drop out? Drop out is, let's say this connection is useless. Okay, sorry. Let's say this connection is useless. This connection is useless. This is useless. This is useless. I don't need these connections. So I remove connections from my network that are not adding any value. Okay. So this is what we do. This is called dropout. We are removing a percentage of our connections that we don't need. We are optimizing our system. And you'll be surprised how accurate your system will be once you do this. It will add at least 2 to 3% of accuracy, not just optimization. So conv2d 16 2 by 2 ReLU input shape, this is it. Then keras layers dropout 0.1. This means you are dropping out 10% of your neural connections. And then another conv2d 32 filters 2 by 2 activation ReLU, and then we do padding equals same so that the output of this layer is matched with the input of the second. We need to do this, okay? Padding equals same.
Sorry, doctor, is it recommended in data series problem to have the same padding or it depends?
No, it depends. It's not a rule. It's not a rule.
Okay, okay.
tf.keras.layers drop out 0.2. Now we are dropping 20%. So as you realize, you are increasing your dropout as you go, because you are going more into detail, and it's more probable that you will have useless connections in later stages. So you can add this. You're gonna say, how did you choose this? What's the thing behind it? Why did you choose 0.5, not 0.1? I'm going to share a code with you, which is a keras tuner code that I wrote. Okay, this keras tuner was actually implemented on the MNIST dataset that is very famous. You can use it and take the functions from it. Using these functions, as you can see, the keras tuner, what you can do is you can loop over the units of the number of units in the dense layer. You can loop over the actual dropout percentages. You can loop over the learning rate, and then you run it. And then finally, it will tell you that the best parameters that you got when you did your hypertuning, it says the hyperparameter search is complete. The optimal number of units in the first layer is this. Optimal learning rate is this. And you can also challenge yourself and do this over all the hyperparameters. It might take you hours, depends on your data. But if you do this, it will, yes, exactly. You can do this in order to choose your parameters wisely and not to say, well, I don't know why I chose it. You can know now. You can say, I did KRAS tuning and I have the highest accuracy, highest precision, highest whatever, depends on your metric, when I use these kinds of parameters or these values. And then you finish this, conf2d drop out, and finally you flatten them to have all of the features on one column and one layer. And then dense 2, because we have a 2 output system. You're gonna say, why is this softmax? Why is this sparse categorical while you have 2 classes? It will work, it will function. However, it should be binary cross entropy, because these are 2. I left it for you guys so that if you have multiple classes to try it out. So this is for multiple classes, more than 2. You can use binary cross entropy in order to test it. So this is the actual model. The summary is this. You write model.compile. You choose the optimizer with the learning rate, the loss function that you will optimize, and the metric that you will be assessing. And finally, you will write history equals model.fit. So I fit my model over X train and Y train, 20 epochs, so it repeats 20 times, over X test and Y test for validation. So I'm going to use X train, Y train to train my system, and X test, Y test to validate. Now comes the suspected or expected thing, which is, look at this. This is my accuracy for training, 0.3, 0.7, 0.95, and then 1, 1, 1, 1, 1, 1, 1. And this is a scenario called in your dreams scenario, or you have messed up so bad scenario. Some people publish, they think, oh, we got 100%, that's excellent. My friend, you overfit your system. You overfit. You should not have 100%. 100% is not healthy. Being able to classify at 100% is not something that you should be proud of. It means that the training data that you used is so much overfit, the system is so much overfit to it that it memorized it so good. Like, why is that? Can't I have high accuracy? Yes, you can. But if you check the validation accuracy, now this is the trick I will give you and end with it. If you have a very high and increasing accuracy of training and your validation is like this, jumping up and down, 0.03, 0.83 at the start, this is not good. It started at 0.83, it went to 1, and then went down, and then it will go back up, and then it will go back down. So I plotted it using matplotlib for you. I plotted the accuracy for validation, the loss, and so on. This is what we get. This is good. This looks good. However, it should not reach 1. It reached 1 over here. And this is your validation. It goes to 1, it goes down. Goes 1, goes down. The typical case should be this goes up and this goes up with it, but not so much. Okay, so the typical curves that you should be seeing if you did a good job are the following. Let me just draw a curve for you. They should be like this. This is your training until 90s, let's say, and this is your validation.
Doctor, just I have one question. Sometime when setting the number of epochs, it's for the graph, it started the fluctuation at the first. However, when changing the number of epochs or raising the number of epochs, it can be go good.
Yes,
after certain epochs.
Yes, that's true. Yes, what you are saying is correct. What you are saying is correct. Your friend is saying that it might have this fluctuation because I only have 10 times or 10 epochs or 20. However, if you do 100 epochs, you will see that this fluctuation is just at the beginning and then it will go fine. That's correct. Okay, that's correct. However, as a rule, if you have an increasing accuracy until training accuracy that reaches 100 and a validation accuracy that is fluctuating like this, probably it will not go fine. It will keep fluctuating, probably. So it's like a rule, if you do not have two validation and training curves that are going together in a let's call it monotonic way, it means that you are overfitting. This is typical overfitting. Why am I overfitting in my application? I reached 100%, but why am I overfitting? Because the patients or subjects that I use are not enough to classify. Okay, so I used 3 subjects. I told you 3 is fine. I got 80%, 100%, but it's not enough. It's not enough, okay? We need more. And I want you guys to try it out. I gave you access to the data sets via PhysioNet. You have the code, try it out. Do your own work and see what gets you. And I'll be glad to have it shared with you. So this is the validation loss. Check this out. This is also weird. The loss gets up like this and down, then up. So these are typical overfitting looking curves. We can try to increase the number of epochs and see where it takes us. However, I do not expect it to give us much different results. I've tried it multiple times, but it might, okay? So in order to take this system now and deploy it, let's suppose it is accurate and precise enough, you can use the TF Lite, okay? TF Lite, TensorFlow Lite, which is a way of optimizing your code. It converts it into just like compressing your file. It takes your model and then it performs some pruning and some optimizations in terms of the number of neurons, numbers of connections, so that it decreases the size and the functions, even the functions that you are using might differ. So not all functions are convertible into TF Lite. Keep it in mind. ما تفكروا دايما انه نحن we can convert any algorithm into TF Lite. It might not convert. You might be using complex models that are not convertible. So you need to figure a way to fix your algorithm or your model before you convert it. And once it is converted into TF Lite, you need some mobile application development skills using Android Studio and so on to be able to create a mobile graphical user interface and a mobile app. And you need some web development to create a web interface. Or you can use Theano over Raspberry Pi to create your ML or AI system. And you can use these Spark Fun Edge. Okay, Spark Fun Edge. This has been out, I think, since 2019 or 2018, maybe a bit before. This is TensorFlow powered. It's powered by TensorFlow. You can just convert into TF Lite and then upload the file onto this Spark Fun Edge and design your own wearable medical devices with enabled AI for your projects. Or you can use the Arduino 33 BLE Sense, okay, which is an Arduino that has accelerometers, gyroscopes, humidity, temperature, altitude meter, all of these embedded into it or onto it. You can use it directly, and you can use the Arduino IDE to write AI codes. You use TF Lite and then you import them. So now it's easier for you to deploy your machine learning algorithms onto hardware. This is all I have to say for this session. Thank you so much for being attentive. I hope that it was useful and beneficial for you guys. You have my email address, so you can send me an email at any time. I can also share my number if you wish. I'm going to write it over here. Okay, so this is my number.
Thank you so much, Dr. Ramzi. The session was really useful for all the participants. So thank you for all of this. We could also share your number on the Discord channel. So thank you everyone for attending all the sessions, and also thank you, Doctor, for your extra time. So we know that you were answering the questions. So as for the participants, this is the end of the Global AI Festival, the MENA AI Festival, part of the Global AI Festival. And we will be sharing all the links on Discord, and will still be available on Discord channel. So stay updated there. And if you have any question on any of the talks or any of the workshop, feel free to interact on Discord channel. And that's it. Thank you, everyone. And have a great weekend. I hope this was beneficial. And thank you so much, Doctor. Have a great weekend. Bye-bye.